Welcome to Sleepless Philosophers, where deep ideas meet restful nights. If you enjoy these journeys through philosophy, please like and subscribe and turn on notifications for daily uploads. To support the channel, consider leaving a super thanks. Any amount helps us continue creating content. You can also become a member to request video topics. We're not monetized, so your support truly makes the difference. Now let the philosophy begin. Epimenides' paradox. A poet from Crete named Epimenides once declared that all Cretans are liars, and this statement, simple as it seems, has echoed through the centuries as one of the earliest recorded paradoxes, a puzzle that predates even the formal study of logic, and yet contains within it the seeds of contradictions that still trouble philosophers today. If Epimenides himself is a Cretan and he claims that all Cretans are liars, then his statement must be a lie. But if his statement is a lie, then not all Cretans are liars, which means some Cretans tell the truth, which could include Epimenides himself, which means his statement might be true after all, which means all Cretans are liars, which means his statement is a lie and the cycle begins again. The paradox is not quite as airtight as the liar paradox that would emerge later, because calling someone a liar does not mean they always lie. Only that they lie sometimes. And so there remains a sliver of logical escape, a possibility that Epimenides is telling the truth on this one occasion while still being a liar in general, or that his statement is partially true and partially false, depending on how it is interpreted. St. Paul referenced the paradox in his letter to Titus, quoting Epimenides and adding that the statement is true, seemingly unaware or unconcerned with the logical contradiction embedded in his endorsement. And this has led to centuries of theological and philosophical debate about what Paul intended and whether Scripture itself contains a paradox. The ancient Greeks recognized the puzzle, but lacked the formal tools to fully analyze it, treating it more as a rhetorical curiosity than a serious threat to logic. And it was not until the development of modern symbolic logic that the deeper implications became clear. The paradox belongs to a family of self-referential statements that collapse under their own weight, and Bertrand Russell would later use variations of this structure to reveal cracks in the foundation of mathematics, proving that not all sets can be safely defined, that not all statements can be assigned a truth value without contradiction. Some philosophers argue that the Epimenides paradox is weaker than its descendants because it depends on empirical facts about Cretans rather than purely logical structure, and that if we simply reject the premise that all Cretans are liars, the paradox dissolves, unlike the pure liar paradox which creates contradiction through its form alone. Others see it as an early recognition that language can turn against itself, that statements about truth and falsehood require careful handling, that self-reference introduces dangers that must be acknowledged and navigated. The paradox also raises questions about identity and generalization, about what it means to make sweeping claims about groups of people, and whether such claims can ever be fully coherent when the speaker is part of the group being described. Epimenides stands at the origin of a long tradition of logical puzzles, his words reverberating through time. A poet who may not have fully understood what he had unleashed, but who nevertheless gave voice to one of the fundamental tensions in human thought, the way that truth can fold back on itself and become strange, unstable, uncertain. Fichte's paradox of knowability. There is an appealing idea in philosophy, a principle that seems to capture something important about truth and knowledge, and this is the knowability principle, which states that all truths are knowable, that for any true proposition there is at least a possible situation in which someone knows that proposition, and this principle seems modest, even Platonic in spirit, suggesting that truth and knowledge are intimately connected, that reality is not fundamentally hidden or inaccessible, that the universe is intelligible in principle, even if not all truths are actually known by anyone, at any given time. The principle distinguishes between what is known and what is knowable, acknowledging that many truths remain unknown, perhaps because no one has investigated them, or because the evidence is lost, or because the relevant questions have not yet been asked, but insisting that these unknown truths could be known, that there is no barrier in principle preventing them from being discovered. And this seems like a reasonable position, neither too strong like the claim that all truths are actually known, which is obviously false, nor too weak like the claim that some truths are unknowable, which seems to concede too much to skepticism and to suggest that reality contains secrets that are forever beyond our reach. But in 1963, Friedrich Fitch proved a shocking result, a theorem showing that if the knowability principle is true, then all truths are actually known, that the modest principle collapses into the absurdly strong claim it was meant to avoid. And this result, known as Fitch's paradox or the knowability paradox, has profound implications for epistemology, the philosophy of language, and debates about realism and anti-realism, and it forces philosophers to choose between giving up the knowability principle, accepting the absurd conclusion that all truths are known, or finding some way to reformulate the principle to avoid the paradox. The proof is elegant and surprisingly simple. Proceeding by reductio ad absurdum, suppose there is a truth that is unknown, call it P, and suppose also that no one knows that P is an unknown truth. That is, no one knows the conjunction P, and P is not known. And now apply the knowability principle, which says that this conjunction, being true, must be knowable, must be such that someone could know it. But here a contradiction emerges, because to know a conjunction, one must know both conjuncts. So to know P and P is not known, one must know P and also know that P is not known. But if one knows P, then P is known, which contradicts the second conjunct that P is not known. And so the conjunction P and P is not known cannot be known. It is an unknowable truth, and this contradicts the knowability principle, and therefore the assumption that there is an unknown truth must be false, and so all truths must be known. The paradox depends on the assumption that knowledge distributes over conjunction, that if you know P and Q, then you know P and you know Q, which seems uncontroversial, and on the assumption that knowledge is factive, that if you know P, then P is true, which is a standard requirement in epistemology, and so the paradox cannot be easily dismissed as relying on dubious principles. It seems to follow from our ordinary understanding of knowledge and knowability, and yet the conclusion is unacceptable. The claim that all truths are actually known is empirically false. There are obviously truths about the distant past, about the far reaches of the universe, about the inner workings of consciousness, that no one knows. And so something must give, either the knowability principle or the reasoning that derives the paradox from it. One response is to reject the knowability principle, to accept that there are unknowable truths, truths that could never be known by anyone under any circumstances. And this is the position of semantic realists, who argue that truth is independent of our capacity to recognize it, that reality outstrips our epistemic abilities, that the world contains facts that are forever beyond our ken. And for realists, the knowability paradox is not a disaster, but a vindication, a proof that the anti-realist commitment to knowability is untenable, that we must accept a more robust conception of truth as radically independent of knowledge. Another response, favoured by anti-realists and verificationists, is to reformulate the knowability principle to avoid the paradox while preserving the intuition that truth and knowability are connected, and various reformulations have been proposed. Some restrict knowability to propositions that do not involve knowledge ascriptions, avoiding the problematic self-referential structure of P and P is not known. Others distinguish between individual and collective knowability, arguing that all truths are knowable by the epistemic community as a whole, even if not by any single individual, and still others embrace a temporal or modal reformulation, claiming that all truths could have been known at some time or in some possible world, rather than claiming that all truths are actually knowable in all circumstances. Some philosophers argue that the paradox reveals a tension in the concept of knowability itself, that knowability is not a simple modal notion, but involves complex interactions between truth, knowledge, and the conditions under which knowledge is possible, and that our intuitions about these interactions are unreliable, pulled in different directions by competing commitments, and so the paradox exposes an instability in our conceptual scheme rather than refuting any particular philosophical position. The paradox also connects to debates about the nature of propositions and the objects of knowledge. Because the problematic conjunction P and P is not known seems strange, it is a proposition about itself in a way, a proposition whose truth depends on whether it is known, and this self-referential or quasi-self-referential structure is reminiscent of the liar paradox and other semantic paradoxes, and some responses to Fichte's paradox draw on strategies developed for dealing with those paradoxes, such as hierarchies of languages, restrictions on self-reference, or non-classical logics that reject certain principles, like the law of excluded middle. The paradox has implications for constructivism in mathematics and logic, because constructivists typically endorse some version of the knowability principle, identifying truth with provability or constructibility, and Fichte's paradox threatens this identification, suggesting that even constructivists must either accept that all mathematical truths are already proved, which is absurd, or abandon the simple identification of truth with provability and develop a more nuanced account of the relationship between the two. The knowability principle, innocent as it seemed, turns out to be a Trojan horse, a seemingly modest claim that conceals a radical commitment, and Fichte's paradox forces philosophers to confront the costs of various epistemological positions, to choose between realism with its unknowable truths and anti-realism with its need to reformulate or restrict the knowability principle, and the paradox remains a central puzzle in contemporary epistemology, a test case for theories of truth and knowledge, a proof that demonstrates with crystalline clarity that even the most intuitive principles can lead to absurdity when their logical consequences are rigorously traced. And it stands as a reminder that philosophy is not merely a matter of articulating and defending intuitions, but of following arguments wherever they lead, even when they lead to conclusions that undermine the very intuitions that motivated them. And the unknown truth, the proposition that is true but not known, sits at the center of the paradox, both knowable and unknowable, possible and impossible, a conceptual anomaly that refuses to be tamed by logic or softened by reformulation. And the paradox endures, a monument to the power of formal reasoning, to reveal deep tensions in our most basic concepts, tensions that no amount of philosophical maneuvering has yet managed to resolve in a way that satisfies all intuitions and preserves all principles. And so the debate continues, philosophers proposing new solutions, new restrictions, new interpretations, and the paradox persists, waiting to trap the unwary, to challenge the confident, to remind us that even truth and knowledge, the twin pillars of epistemology, are stranger and more problematic than they first appear. McTaggart's paradox of time, why past, present, and future are contradictory. A philosopher named J.M.E. McTaggart constructs an argument attempting to prove that time is unreal, that temporal distinctions are contradictory, that past, present, and future cannot coexist, and the argument begins by distinguishing two ways of thinking about time: the A series, which orders events as past, present, or future, and the B series, which orders events as earlier than or later than each other. And McTaggart argues that the A series is essential to time, that change requires events to move from future to present to past, that without this passage, Without the A series, there is no real time. But the A series is contradictory, generates logical problems, and therefore time is unreal, is an appearance generated by our temporal perspective, but does not correspond to ultimate reality. And this is McTaggart's paradox of time, one of the most famous and most controversial arguments in the philosophy of time, an argument that has shaped all subsequent debates about the nature of time, about whether time is real or illusory, about whether the passage of time is objective or subjective. Imagine time as having two aspects: the A series aspect, where events are classified as past, present, or future, where we say the meeting is future, is happening now in the present, was past yesterday, and events change their A series position, move from future to present to past, and this movement is time's passage, is what makes time dynamic. And the B series aspect, where events are ordered as earlier or later, where we say the meeting is later than breakfast and earlier than dinner, and these B series relations are fixed, do not change. The meeting is always later than breakfast, regardless of when we consider it. And McTaggart argues that the A series is essential for real time, that the B series alone is not sufficient, that time requires passage, requires events to change from future to present to past, but the A series is contradictory, and so time is impossible, is unreal. The paradox emerges from the fact that A series properties are contradictory. Every event is past and present and future. The meeting is future before it occurs, is present when it occurs, is past after it occurs. And so the meeting has all three properties, is past and present and future. And these properties are incompatible, cannot all be instantiated by the same event. And so the A series generates contradiction. And the standard response is to say that events have A series properties at different times. The meeting is future at earlier times, present at its time of occurrence, past at later times. And this seems to resolve the contradiction by indexing A series properties to times. But McTaggart argues this does not help, because now we must ask whether the times themselves are past, present, or future. And the same problem recurs. If the time at which the meeting is future is itself past, then the meeting is past and future, and contradiction remains. And indexing to times does not eliminate the contradiction, but only pushes it back. McTaggart argues that the only way to avoid contradiction is to eliminate the A series, to accept that events do not really move from future to present to past. That passage is illusory, that reality consists only of the B series, only of earlier-later relations. But the B series without the A series is not real time, is only a static ordering, lacks the dynamism, lacks the passage that is essential to time. And so time is unreal, is an appearance that our consciousness generates from a fundamentally timeless reality. And McTaggart's position is a form of idealism about time, treats time as mind-dependent, as not part of the ultimate structure of reality. Visualize the paradox as a vicious circle. Events have A series properties, but these properties are contradictory. So we index them to times, but then times have A series properties, which are contradictory. So we index to second-order times, but these are contradictory, and the regress continues, and the contradiction is never eliminated, only relocated. And McTaggart concludes that the A series is inherently contradictory, cannot be made coherent, and must be rejected. And with it goes time itself, which requires the A series for its reality. One response to McTaggart's paradox, the tenseless or B theory response, accepts McTaggart's argument that the A series is contradictory, but denies that time requires the A series, argues that the B series is sufficient for real time, that earlier-later relations constitute time, and passage is an illusion, is a feature of our temporal perspective, and the universe exists as a four-dimensional block, a block universe where all times are equally real, and past, present, and future are not objective features of reality, but are indexical, are relative to a perspective. And this B theory has become orthodoxy in philosophy of time, is widely accepted as avoiding McTaggart's paradox while preserving the reality of time. Another response, the tense or A-theory response, denies that the A-series is contradictory, argues that McTaggart's argument involves a mistake, that A-series properties are not really contradictory because they are indexed to times in a non-problematic way, and the meeting being future at T1 and past at T2 is not contradictory, is just the normal way temporal properties work. And A-theorists argue that passage is real, that the present is objectively real, that the future is open and the past is fixed. And McTaggart's argument fails because it assumes that A-series properties must be simultaneous to be contradictory when they are not simultaneous, are at different times, and this response preserves the A-series, preserves passage, and rejects McTaggart's conclusion that time is unreal. A third response from presentism argues that only the present exists, that past and future are unreal, and so events do not have contradictory A-series properties because only present events exist, and only present properties are real, and the meeting is not simultaneously past, present, and future because only one of these is real at any time. And presentism avoids McTaggart's paradox by radical ontological restriction, by accepting that most of time does not exist, and this preserves the reality of the present, preserves passage, but faces difficulties explaining how truths about past and future can be true if past and future do not exist. McTaggart's paradox has been enormously influential, has shaped all debates about time, has forced philosophers to clarify their positions, to distinguish A theories from B theories, to recognize that different conceptions of time have different metaphysical commitments, and the paradox remains controversial, remains debated, with some accepting McTaggart's conclusion that time is unreal, some accepting that the A series is contradictory, but denying that this makes time unreal, and some denying that the A series is contradictory, and no consensus exists, and the paradox endures as one of the most important arguments in metaphysics, an argument that challenges our ordinary understanding of time, forces recognition that temporal passage, the movement from future through present to past, is philosophically problematic, and whether time is real or illusory remains one of philosophy's deepest questions. And McTaggart's paradox continues to structure the debate, continues to force philosophers to grapple with the nature of time, with whether passage is objective or subjective, with whether reality is a static four-dimensional block or a dynamic unfolding present, and the paradox persists, unsolved and perhaps unsolvable, a permanent challenge to theories of time. Goodman's Grue paradox. When emeralds turn blue at midnight, a philosopher invents a new colour term, grue, and grue is defined as follows. An object is grue if it is observed before time t and is green, or if it is not observed before time t and is blue, where t is some future date, perhaps January 1st of next year. And this definition is strange, is artificial, combines observation and time in a way that ordinary colour terms do not. But the definition is precise, is perfectly clear. And now the philosopher considers emeralds and notes that all emeralds observed so far have been green. And these observations support the hypothesis all emeralds are green. And the same observations also support the hypothesis all emeralds are grue because all observed emeralds satisfy both descriptions. They are green, which means they are grue up to time t, and both hypotheses are equally well supported by the evidence. Both fit all observations perfectly, and yet the two hypotheses make different predictions about the future. The first predicts that emeralds examined after time t will be green. The second predicts they will be blue. And so we have two hypotheses, equally supported by evidence, making opposite predictions. And the question is, which hypothesis should we believe? Which generalization should we project into the future? And Nelson Goodman poses this as a problem about projectability, about which predicates can legitimately be used in inductive inferences. And this is the Grue paradox. also called Goodman's new riddle of induction, a puzzle that shows that not all evidence-supported hypotheses are equal, that some predicates are projectable and others are not, and the challenge is to explain what makes green projectable and GRU not, what distinguishes legitimate from illegitimate generalizations. Imagine living in a world where emeralds are GRU, where all emeralds observed before time t are green, but all emeralds examined after time t are blue. And from the perspective of someone before time t, this is indistinguishable from a world where emeralds are simply green. All observations are the same, and yet the two worlds are radically different, will diverge dramatically after time t. And the puzzle is that evidence accumulated before t does not distinguish between these possibilities, does not tell us which world we inhabit, and so induction alone cannot determine which hypothesis to accept, cannot tell us whether emeralds are green or GRU. And this reveals that induction requires more than just fitting evidence, requires principles about which predicates are projectable, which generalizations are legitimate. And these principles cannot themselves be justified inductively without circularity. Visualize the timeline with time t marking a boundary, and on one side of the boundary, all observed emeralds are green. And the question is what happens after the boundary. Do emeralds remain green, or do they become blue? And the hypothesis, all emeralds are GRU, says they switch colours. But this switching is built into the definition of GRU, is a feature of how the predicate is defined rather than a feature of emeralds themselves. And this reveals something important, that the GRU hypothesis is gerrymandered, is artificially constructed to fit past observations while making a different prediction about the future. And our intuition is that such gerrymandered hypotheses should not be projected, should not be taken seriously, but explaining why requires articulating a principle that distinguishes natural from gerrymandered predicates. Goodman's own solution appeals to entrenchment, argues that green is projectable because it has been used successfully in many past inductions, has become entrenched in our language and our theories, while GRU is a newcomer, is defined artificially, has no history of successful projection, and so we should prefer green over GRU, not for any logical reason, but for pragmatic reasons, because green has proven its worth. And this solution ties projectability to linguistic and scientific practice, makes it a matter of history rather than logic. And some find this unsatisfying, find it too relativistic. But Goodman argues that there is no deeper justification available, that entrenchment is as good as justification gets for inductive inference. Another response argues that GRU is not a genuine predicate, is not natural, because it is defined in terms of observation and time, includes reference to specific moments and observers, and genuine properties should be observer-independent, should not change based on when or whether they are observed. And green is natural in this sense, refers to a real property that objects have regardless of observation, while GRU is artificial, is defined through disjunction and reference to observation, and so only natural predicates are projectable. And this solution requires explaining what makes a predicate natural, what distinguishes genuine properties from artificial constructions. And this leads to metaphysical questions about the nature of properties, about whether naturalness is objective or conventional. A third response from a Bayesian perspective argues that GRU hypotheses are less probable than green hypotheses given reasonable priors, because GRU hypotheses postulate discontinuities, postulate that properties change suddenly at arbitrary times, and such discontinuities require explanation, require reasons, and in the absence of such reasons we should assign low prior probability to GRU hypotheses. And so while GRU fits the evidence as well as green, GRU is less probable overall because of its lower prior, and this solution appeals to simplicity and parsimony, treats continuous properties as more probable than discontinuous ones, and explains projectability in terms of prior probabilities rather than entrenchment or naturalness. The Grue paradox also reveals that the problem of induction is deeper than Hume recognized, because Hume worried about justifying any inductive inference, about showing that the future will resemble the past. But even if we accept induction, we face Goodman's problem. We must choose which respects the future will resemble the past, must decide which predicates to project, and different choices lead to different predictions. And there is no algorithm, no mechanical procedure that tells us which predicates are projectable, which generalizations are legitimate. And so induction requires judgment, requires background knowledge, requires engagement with the actual practice of science rather than pure logical analysis. The paradox extends beyond emeralds and colours to any inductive inference, to all attempts to generalize from observed to unobserved cases, because for any pattern we observe, for any regularity we find, there are infinite Grue-like predicates that fit the pattern up to now, but diverge in the future, and choosing between these predicates cannot be done on evidential grounds alone, requires additional principles, requires distinguishing projectable from non-projectable predicates. And every scientific theory makes such choices, implicitly assumes that certain predicates are natural and others artificial. And Goodman's paradox makes these assumptions explicit, forces recognition that induction is not just about fitting evidence, but about choosing the right vocabulary, the right predicates, the right way of carving up the world. The clock approaches time T, and emeralds remain green, as they always have been, and the Grue hypothesis is refuted, is shown to have been wrong. But before time T, the evidence supported Grue as much as green, and this shows that evidence alone was insufficient, that something beyond evidence guided our preference for green, our confidence that emeralds would remain green rather than turning blue, and that something is what Goodman's paradox investigates, what it challenges, used to articulate, and the paradox remains not fully resolved, not answered by any single theory that satisfies everyone, but persistent as a challenge to theories of induction, a test case for accounts of scientific reasoning, and a reminder that generalizing from experience requires more than logic, requires substantive assumptions about the world, about which properties are real and which are artificial, about which patterns will continue and which will break. And these assumptions cannot be justified inductively without circularity, cannot be proven logically without begging the question. And so induction rests ultimately on judgment, on practices that have proven successful, on entrenchment or naturalness or simplicity. And Goodman's Grue paradox reveals this foundation, exposes the principles we rely on but cannot fully justify. And the paradox endures as one of the most important problems in philosophy of science. Libet's experiments. Paradox: why your brain decides before you do. A neuroscientist named Benjamin Libet designs an experiment to investigate the timing of conscious decision-making, to discover when conscious intention arises relative to brain activity and action. And subjects sit before a screen with a moving dot like a clock hand, and they are instructed to flex their wrist whenever they feel like it, spontaneously, without planning in advance. And while they watch the screen, they note the position of the dot when they first become aware of the intention to move, when they first consciously decide to flex. And meanwhile, electrodes measure brain activity, specifically measure the readiness potential, a build-up of neural activity that precedes voluntary movements. And Libet's finding is striking and controversial. The readiness potential begins several hundred milliseconds before the subject reports conscious awareness of the intention to move. The brain activity precedes conscious intention by about 300 to 500 milliseconds. And this seems to show that the brain decides to move before consciousness decides. That unconscious neural processes initiate the action, and conscious intention is a kind of afterthought, an epiphenomenon, something that arises after the decision has already been made at the unconscious level. And this finding appears to challenge free will, appears to show that conscious decisions do not cause actions but merely accompany them or follow them. And this is Libet's experiment's paradox. the discovery that our conscious intentions come too late to cause our actions, come after the brain has already committed to acting, and this creates philosophical puzzles about the nature of volition, about whether we truly initiate our actions or merely become aware of them after unconscious processes have already set them in motion. Imagine the subject in Libet's experiment, watching the dot move around the screen, waiting for the urge to flex their wrist, and suddenly they feel the intention. They become aware of wanting to move, they experience the conscious decision, and they note the position of the dot. And a moment later, their wrist flexes, and this sequence feels like the intention caused the movement, feels like they decided consciously and then acted. But the brain recordings tell a different story, show that neural activity associated with the movement began several hundred milliseconds before the conscious intention that the brain was preparing to move, before consciousness knew about it. And this temporal order suggests that consciousness does not initiate action, but only monitors it, only becomes aware of decisions that have already been made unconsciously. And if this is correct, then conscious free will is an illusion, is a feeling that arises after the fact, after unconscious processes have already determined what will happen. The paradox is that subjectively, we feel like we consciously decide and then act, feel like conscious intention is the cause of action, but objectively, the neural evidence suggests that unconscious processes cause both the action and the conscious intention, that consciousness is not in the driver's seat but is a passenger, observing but not controlling, and this disconnect between subjective experience and objective reality creates the paradox, makes us wonder whether free will is real or illusory, whether we are agents who initiate actions or spectators who witness actions that our brains have already decided to perform. Visualize the timeline. At time 0, the readiness potential begins. Unconscious neural activity starts building up. At time 300 milliseconds, the subject becomes consciously aware of the intention to move. At time 500 milliseconds, the movement occurs. And the critical question is what causes what? Does the conscious intention at 300 milliseconds cause the movement at 500? Or does the unconscious readiness potential at time 0 cause both the conscious intention and the movement? And Libet's data suggests the latter, suggests that unconscious brain activity is the real cause, is the initiator, and conscious intention is just another effect, another consequence of the unconscious process. And if this is right, then conscious will is causally inert, does not actually produce behavior, is epiphenomenal. Many philosophers and scientists have challenged Libet's interpretation. One response questions the measurement of conscious intention, argues that asking subjects to note when they became aware of intending is asking them to introspect a process that might not be accessible to introspection, and the reported time of intention might be inaccurate, might be systematically delayed, and subjects might become aware of intending earlier than they report, perhaps at the same time as the readiness potential begins. And if conscious awareness actually coincides with the readiness potential, then there is no paradox. Consciousness is part of the initiating process, not an afterthought. Another response distinguishes between different kinds of decisions, argues that Libet's experiments involve arbitrary decisions, spontaneous movements without specific goals or reasons, and these are not typical of the kinds of decisions we care about when discussing free will. And meaningful choices, choices based on deliberation and reasons, might involve different neural processes, might involve consciousness more centrally. And Libet's findings about arbitrary wrist flexions do not generalize to all decisions, do not show that conscious deliberation is always epiphenomenal, and free will might be preserved for rational choices even if spontaneous impulses are unconsciously initiated. A third response questions the interpretation of the readiness potential, argues that early neural activity does not necessarily represent a decision or commitment to act, but might represent preparation, might be part of the process of forming an intention rather than being the cause of intention, and consciousness might be involved throughout this process. And the readiness potential and conscious intention might be parts of a single, integrated process rather than separate causes. And Libet's interpretation assumes too sharp a separation between unconscious and conscious processes, treats them as competing causes when they might be cooperative aspects of a single decision-making system. Some philosophers embrace Libet's findings, argue that they confirm what we should have known all along, that consciousness does not have magical causal powers, that all mental processes are brain processes, and brain processes are physical processes that operate according to causal laws, and conscious states are aspects of brain states, not separate entities that somehow reach into the physical world to cause behavior. And Libet's experiments help dispel the Cartesian illusion that consciousness is a separate substance with independent causal power, help show that we are physical beings whose actions are caused by physical brain processes, and consciousness is part of this physical system, not a separate controller. Libet himself proposed that consciousness might not initiate actions, but might have a veto power, might be able to stop actions that unconscious processes have initiated. And he found some evidence for this, found that conscious intention could inhibit movements, even after the readiness potential had begun. And this veto function preserves a role for conscious will, makes consciousness a gatekeeper, if not an initiator. And this preserves some form of free will, free won't rather than free will, the ability to consciously inhibit unconsciously initiated impulses. The experiments have been repeated and refined by many researchers, with various results, some confirming Libet's findings and others qualifying them, showing that the relationship between brain activity, conscious awareness, and action is more complex than Libet's original interpretation suggested, and the debate continues with no consensus about what the experiments show about free will, about whether they undermine it or are compatible with it. And the paradox persists as a live issue in neuroscience and philosophy. The subject flexes their wrist, notes the time of intention, and the electrodes record the readiness potential, and the timing reveals that brain activity preceded awareness. And the question remains what this means for free will, whether it shows that consciousness is epiphenomenal, that we do not truly initiate our actions, or whether the interpretation is wrong, whether consciousness is involved earlier than subjects report, or whether the experiments test the wrong kinds of decisions. And Libet's paradox endures as one of the most discussed and controversial findings in the neuroscience of volition, a set of experiments that appears to show that free will is an illusion, that our conscious sense of agency is a feeling that arises after decisions have already been made, and whether this appearance is accurate, whether the paradox is real or illusory, remains one of the most important questions at the intersection of neuroscience and philosophy. And the readiness potential builds, and consciousness awakens, and action follows, and the temporal order creates the paradox, and the debate continues. Grandi's series, when adding numbers, forever gives multiple answers. A simple mathematical series begins with 1 minus 1 plus 1 minus 1 plus 1 minus 1, continuing forever without end, alternating between adding 1 and subtracting 1. And the question emerges, what does this infinite sum equal? What value does it approach as more and more terms are added? And the paradox is that different methods of calculation give different answers, each seemingly valid, each following mathematical rules, yet reaching contradictory conclusions. And this is Grandi's series, named after the Italian mathematician Guido Grandi, who studied it in the early 18th century. And the paradox reveals fundamental questions about what it means to sum an infinite sequence, about whether all infinite series have definite values, and about the limits of algebraic manipulation when dealing with infinity. Consider the series visually. Imagine a number line where you start at 0, then move 1 unit to the right to reach 1, then move 1 unit to the left back to 0, then 1 unit right to 1 again, then 1 unit left to 0, and this pattern continues forever, oscillating between 0 and 1, never settling down, never approaching a limit in the traditional sense, and so, from this perspective, the series does not converge, does not have a sum. The partial sums bounce between 0 and 1 eternally and never stabilize. But now consider a different approach. Group the terms in pairs, taking 1 minus 1 as the first pair, which equals 0, then 1 minus 1 as the second pair, also 0, and so on. And the series becomes 0 plus 0 plus 0, continuing forever. And the sum of infinitely many zeros is 0. And so by this grouping method, the series equals 0. And this seems like a valid manipulation. Grouping terms is a standard algebraic operation, and yet it produces a definite answer where the oscillating view produced no answer. Now consider another grouping. Start by leaving the first one alone, then group all subsequent pairs, so the series becomes 1 plus the quantity negative 1 plus 1, then the quantity negative 1 plus 1, and so on, and each grouped pair equals 0. So the series becomes 1 plus 0 plus 0 plus 0, continuing forever. And this equals 1, and so by this different grouping, the series equals 1 instead of 0. And both groupings seem legitimate. Both use standard algebraic rules, yet they produce different answers, 0 and 1. And this is the heart of Grandi's paradox, that the series is sensitive to how it is manipulated, that rearranging or regrouping terms changes the result. And this suggests that the series does not have a well-defined sum in the ordinary sense. Mathematicians have developed sophisticated tools to handle divergent series, like Grandi's, and one approach is Cesaro summation, which assigns values to series by averaging the partial sums. And for Grandi's series, the partial sums are 1, 0, 1, 0, 1, 0, continuing to alternate, and the average of the first n partial sums approaches 1/2 as n grows large, because roughly half the partial sums are 1 and half are 0. And so by Cesaro summation, Grandi's series equals 1/2, and this method produces yet another answer, neither 0 nor 1, but the midpoint between them. And this answer has a certain aesthetic appeal. It represents the average behaviour of the series, the value around which it oscillates, and it can be justified by analogy to functions. If you consider the geometric series 1 minus x plus x squared minus x cubed and so on, which converges to 1 over 1 plus x for absolute value of x less than 1, and you plug in x equals 1, you get 1 over 2. And so in some extended sense, Grandi's series can be said to equal 1/2. The paradox reveals that divergent series do not have sums in the way convergent series do, that assigning values to them requires making choices about what summation method to use, and different methods give different results. And there is no single correct answer, but rather a family of possible values, depending on the context and the techniques employed. And this multiplicity is not a flaw in mathematics, but a feature, a recognition that infinite sums are more subtle than finite sums, that operations that work for finite cases can break down or become ambiguous when extended to infinity. Grandi's series appears in physics and engineering, in Fourier analysis, where oscillating sums arise naturally, in quantum field theory, where divergent series are regularized using techniques similar to Cesaro summation, and in signal processing, where alternating patterns must be analyzed. And in these applications, the choice of summation method is guided by physical considerations, by what gives useful predictions, by what aligns. With experimental results, and the paradox becomes less troubling, less a contradiction, and more a reminder that mathematical tools must be adapted to fit the problem, that formal manipulation must be tempered with judgment about what makes sense in context. The series also appears in philosophical discussions about infinity, about whether infinite processes can be completed, about whether the phrase, sum of infinitely many terms, has a determinate meaning or depends on conventions and choices. And Grandi's series suggests the latter, that infinity introduces ambiguities that finite mathematics avoids, that extending concepts from finite to infinite is not automatic but requires care, requires new definitions, requires acceptance that some questions have multiple answers or no answer at all, depending on how they are framed. Imagine watching someone walk back and forth on a path, taking one step forward, then one step back, then one step forward, then one step back, forever without stopping. And you're asked where they end up, and the answer is that they do not end up anywhere. They continue oscillating. But if you ask where they are on average, you might say they're halfway between the two endpoints. And if you ask where they are after an even number of steps, you say at the start. And after an odd number, you say one step forward, and none of these answers is wrong. Each captures a different aspect of the situation, and Grandi's series is similar. Different questions about the series have different answers, and the paradox arises from expecting a single answer when the situation is inherently ambiguous, when the infinite oscillation resists reduction to a single number. The series continues, 1 minus 1 plus 1 minus 1, terms alternating forever, and the sum is 0 or 1 or 1/2 depending on how you calculate it, depending on what method you use, depending on what question you're really asking. And the paradox endures, a simple series that exposes deep issues about infinity, about summation, about the limits of algebraic manipulation, and about the need for careful definitions when dealing with infinite processes. And Grandi's series remains a teaching tool, a cautionary tale, a reminder that infinity is subtle, that divergent series require special handling, and that mathematics is not just calculation, but interpretation, not just following rules, but understanding when rules apply and when they break down. And the series oscillates, forever unresolved, forever producing different answers, and the paradox persists, elegant and instructive, a monument to the strangeness of infinity and the care required when extending finite concepts to the infinite realm. Laplace's demon, the mind that knows everything that will ever happen. A supremely intelligent being, a vast intellect that knows the position and velocity of every particle in the universe at a single instant, stands outside time and space. And this being, this demon, as Pierre-Simon Laplace called it in 1814, possesses the complete laws of physics, the equations that govern how particles interact and move, and with this information, the precise state of every atom and the exact rules of motion, the demon can calculate the future, can determine with perfect accuracy where every particle will be at any future time, can predict every event, every thought, every decision, every outcome, from the fall of a raindrop to the rise of civilizations, from the collision of atoms to the death of stars. And in principle, the demon could also calculate the past, could trace every particle's trajectory backward to determine exactly how the present arose from previous states. And so this demon, given sufficient computational power, could know everything that has happened and everything that will happen, the entire history of the universe, past and future, encoded in a single snapshot of the present. And this is Laplace's demon, a thought experiment about determinism, about whether the universe is a clockwork mechanism, where the future is entirely determined by the past, where free will is an illusion, where everything that will ever happen is already decided, already implicit in the current state of things. Imagine the demon's knowledge as a vast table, infinitely long, listing the position and velocity of every particle, every electron, every quark, every photon, trillions upon trillions upon trillions of entries, and the demon has access to all this information perfectly, knows it exactly, with infinite precision. And the demon also knows Newton's laws, or perhaps Einstein's field equations, or quantum mechanics, knows the rules that govern how these particles influence each other, how forces propagate, how energy transfers. And with this knowledge, the demon can simulate the universe, can run the equations forward in time, calculating step by step how the particles will move, how they will collide and interact, and the simulation produces a prediction, a complete specification of the universe at every future moment. And this prediction, if the laws of physics are deterministic, is not probabilistic but certain. The future is determined, fixed, inevitable, and the demon knows it all. The implications are profound and troubling, because if Laplace's demon is possible, if the universe is deterministic, then free will becomes problematic, becomes perhaps an illusion, because every decision you make, every thought you have, every action you take is the result of particles in your brain following physical laws, and those particles are moving according to rules determined by their initial conditions, and those initial conditions were set by earlier states, going back to the beginning of the universe. And so your choices are not free but predetermined, decided billions of years ago when the universe began, and you are not an agent but an automaton, a complex machine that operates according to fixed rules, and the feeling of making choices, of deliberating and deciding, is a subjective experience produced by computational processes in your brain. But the outcome was never in doubt, was determined from the start, and this conclusion undermines moral responsibility, undermines the concepts of praise and blame, undermines the notion that people could have done otherwise, and it raises the question of what it means to be human if our actions are all predetermined. But Laplace's demon faces several obstacles, several reasons why even in principle it might be impossible. The first obstacle is quantum mechanics, which was unknown in Laplace's time, but is now recognized as fundamental to physics, and quantum mechanics is probabilistic, not deterministic. The Heisenberg uncertainty principle states that we cannot know both the position and velocity of a particle with perfect precision. There is an irreducible indeterminacy, a fundamental limit on what can be known, and when we measure a quantum system, the outcome is random, governed by probabilities but not determined. And so Laplace's demon cannot have the precise initial conditions it needs, cannot know the exact state of the universe, and even if it could, the laws of quantum mechanics only predict probabilities for future events, not certainties, and so the future is genuinely open, not determined, and Laplace's demon is impossible. The second obstacle is chaos sensitivity to initial conditions, where tiny unmeasurable differences in starting states lead to vastly different outcomes over time. Weather systems, planetary orbits, fluid flows, all exhibit chaotic behavior, where prediction becomes impossible beyond a certain time horizon, because errors in measurement, no matter how small, grow exponentially and eventually dominate. And even if quantum mechanics were not an issue, even in a classical deterministic universe, practical prediction would be impossible for chaotic systems, and the demon would need infinite precision, infinitely accurate knowledge of initial conditions, and any finite approximation, no matter how good, would fail after sufficient time. And so the demon's predictions would be useless for complex systems on long timescales. The third obstacle is computational. Even if the demon had perfect information and deterministic laws, simulating the universe requires computing power, requires processing the interactions of every particle, and the universe contains roughly 10 to the 80 particles, and computing their evolution requires resources, and some physicists have argued that simulating the universe would require a computer as large as the universe itself, and such a computer could not run faster than the universe it simulates, could not predict the future faster than the future unfolds, and so the demon could not tell you tomorrow's events before tomorrow arrives, and the demon becomes useless as a predictor, reduced to a mere recorder that reconstructs what has already happened, rather than foretelling what will happen. Visualize the universe as a vast machine, gears turning, particles moving, and Laplace's demon standing outside, watching the machine, knowing the position of every gear, the velocity of every component, and calculating how the machine will continue to turn. But the demon is blocked by quantum uncertainty, cannot measure the gears precisely enough, is blocked by chaos, cannot maintain accuracy over time, is blocked by computational limits, cannot perform the calculation fast enough, and so the demon mighty as it seems, is impossible. The universe resists total prediction, resists complete knowledge, not because of practical limitations, but because of fundamental features of physical law and determinism, even if it were true, does not grant us the power to predict. And the demon remains a thought experiment, a symbol of a kind of knowledge that cannot exist, a vision of omniscience that is ruled out by the nature of reality itself. Laplace's demon also raises philosophical questions about explanation and understanding, because even if we cannot predict the future, even if determinism fails or the demon is impossible, we still seek to explain why things happen, to trace causes and effects, to understand the mechanisms that generate events. And this explanatory project does not require Laplacian determinism, does not require perfect prediction, but only patterns, regularities, laws that hold approximately, and science proceeds without the demon, without omniscience, by finding partial explanations, probabilistic models, statistical regularities, and these are sufficient for understanding, for technology, for navigating the world. And the demon's impossibility does not doom science but liberates it, frees it from the burden of total prediction, allows it to focus on what can be known rather than lamenting what cannot. The demon sits in conceptual space, all-knowing and impotent, knowing everything but unable to act, unable to exist, blocked by uncertainty, by chaos, by computation. And Laplace's vision of a deterministic clockwork universe fades, replaced by a more subtle picture, a universe governed by laws but not wholly determined, open to chance, to randomness, to emergence, where the future is not written in the present but unfolds through processes that are partly lawful and partly random, and free will, though not proven, is at least not obviously refuted, and moral responsibility, though challenged, survives because even if determinism were true, even if all actions are caused by prior states, we still distinguish between actions that flow from deliberation and those that do not, between agents who respond to reasons and those who do not, and these distinctions matter, ground our practices of praise and blame. And Laplace's demon, impossible and paradoxical, remains a touchstone in debates about determinism, free will, and the limits of knowledge. A thought experiment that has shaped centuries of discussion and continues to challenge our understanding of what it means to predict, to know, and to be free. Parfit's teletransportation paradox. Imagine a future where technology allows instant travel across vast distances through a process called teletransportation. A device scans your body down to the atomic level, recording the exact position and state of every particle, and then transmits this information to a distant location where another device reconstructs you perfectly, assembling a body atom by atom according to the transmitted blueprint. And the reconstruction is flawless, every memory intact, every scar reproduced, every thought continued, and the reconstructed person steps out of the receiving chamber, believing themselves to be you, feeling no discontinuity, no sense that anything strange has occurred. The philosopher Derek Parfit asked a disturbing question about this process. Are you the person who steps out of the receiving chamber, or did you die in the scanning chamber? And a copy, a duplicate with all your memories and personality, is now living your life. And if the scanning process destroys the original body as it records the information, then perhaps it is still you, continuous in some sense. But what if the original body is not destroyed? What if the scanner leaves you standing in the departure chamber, intact and alive, while the reconstruction appears in the receiving chamber? And now there are two of you, both with equal claim to being the original, both feeling that they are you, and if both are you, then identity has become plural. But if only one is you, then which one and what criterion could possibly distinguish them when they are physically and psychologically identical? Parfit used this thought experiment to challenge the intuition that personal identity is what matters in survival, arguing that what matters is not identity, not being numerically the same person, but rather psychological continuity and connectedness, the preservation of memories, personality, beliefs, desires, and ongoing projects. And if these are preserved, then survival has occurred even if strict identity has not. And so, the reconstructed person is you in every way that matters, even if they are not numerically identical to the original you. And the question of whether identity is preserved is a question about what we care about rather than a deep metaphysical fact. The paradox becomes more troubling when variations are introduced. Suppose the teletransportation device malfunctions and creates not one, but two reconstructions, both perfect, both claiming to be you, and now identity must branch, which seems impossible because identity is supposed to be a one-to-one relation. A thing is identical only to itself, and yet both reconstructions have an equal claim. And if identity is not preserved in this case, then why should it be preserved in the normal case where only one reconstruction appears? And if it is not preserved, then every time you use the teletransporter, you die, and a new person with your memories takes your place, living a life they falsely believe is a continuation of yours. Parfit embraced the conclusion that identity is not what matters, that we should care about psychological continuity rather than numerical identity, and that the concept of a persisting self, a single unified person who endures over time, is less important than we ordinarily think. That what makes your future self matter to you now is not that they are literally the same person, but that they are psychologically connected to you in the right ways, and if those connections can branch or spread across multiple individuals, then so be it. Identity is not sacred, not the ultimate ground of value or concern. The teletransportation paradox has implications for how we think about personal survival, about whether what matters in death is the cessation of psychological continuity or the cessation of biological life, about whether uploading consciousness to a computer or creating digital copies would constitute survival or merely the creation of simulacra, and about whether the self is a metaphysical entity or a convenient fiction we use to organize experience. The paradox also challenges intuitions about moral responsibility, because if identity is vague or plural, then questions about who is responsible for past actions or who deserves future rewards become murky, and the unity of the person, which underpins much of ethics and law, begins to dissolve. Parfit's teletransportation scenario remains one of the most powerful thought experiments in philosophy, a story that uses imaginable technology to expose deep questions about identity, survival, and what it means to be a person, forcing recognition that the boundaries of the self, like the boundaries of clouds and cats, may be far less clear and far less important than common sense suggests, and that the question of whether you survive. Teletransportation may have no determinate answer, or many answers, or may simply be the wrong question to ask. Meinong's paradox, where non-existent objects live. A philosopher named Alexius Meinong proposes a strange theory, a theory about objects that do not exist, and Meinong argues that there are objects that do not exist, but still have properties, can be talked about, can be thought about, and these non-existent objects populate what Meinong calls the realm of being, a broader category than existence, and examples include the Golden Mountain, which does not exist but is golden and is a mountain, and the round square, which does not exist but is round and square, and Sherlock Holmes, who does not exist but is a detective and lives on Baker Street. And Meinong's theory says we can make true statements about these non-existent objects, can say truly that the Golden Mountain is golden, even though no Golden Mountain exists, and this creates paradoxes, creates puzzles about the nature of reference and truth. Because how can statements about nothing be true? How can non-existent objects have properties? How can we refer to what does not exist? And this is Meinong's paradox, the puzzle about non-existent objects, about whether they are real in some sense, whether being is broader than existence, whether there are things that do not exist but still have some kind of reality, and this paradox has generated enormous discussion, has led some philosophers to defend Menon's theory in modified form and others to reject it entirely, to argue that non-existent objects are impossible, are contradictions, and all objects that can be thought about must exist in some sense. Imagine thinking about Sherlock Holmes, picturing the detective, his deerstalker hat, his pipe, his address at 221B Baker Street, and you're thinking about something. Your thoughts have content, have an object, and that object is Sherlock Holmes. But Sherlock Holmes does not exist, was never a real person, is a fictional character invented by Arthur Conan Doyle. And so, what are you thinking about when you think about Sherlock Holmes? What is the object of your thought? And Menon says the object is Sherlock Holmes himself, a non-existent object, an object that has properties like being a detective and living on Baker Street but lacks the property of existence. And this seems to make sense of how we can think about fictional characters, how we can make true statements about them, but it creates problems because it seems to commit us to a vast ontology of non-existent objects. All the fictional characters, all the impossible objects like round squares, all the merely possible objects that could exist but do not. And this ontology seems bloated, seems to violate parsimony, seems to multiply entities beyond necessity. The paradox sharpens when we consider impossible objects, objects like the round square, which is both round and square, and these properties are incompatible, cannot both be instantiated by a single object. And yet Menon's theory seems to allow that the round square is both round and square, has both properties despite their incompatibility, and this violates the law of non-contradiction, seems to allow contradictions to be true. And Russell famously criticized Menon for this, argued that the round square both exists and does not exist. Exists because it has properties and things with properties must exist to have them, and does not exist because that is part of its characterization. And this contradiction shows that Menon's theory is incoherent, cannot be accepted, and non-existent objects are impossible, and all talk of them must be reinterpreted as talk of something else, talk of ideas or words or possible worlds, but not talk of actual non-existent objects. Visualize Menon's ontology as having two realms, the realm of existence containing actual objects, like tables and mountains and people, and the realm of being containing all objects, including non-existent ones like golden mountains and fictional characters, and the realm of being is vastly larger, contains everything we can conceive, all possibilities and impossibilities, and only a tiny subset of being also has existence. And Menon's theory says that statements can be true of objects in the realm of being whether or not those objects exist, and truth is not restricted to existing objects. And this solves certain puzzles about reference, about how we can refer to what does not exist, but creates the paradox of how non-existent objects can have properties, can be subjects of true predications when there is nothing there to have the properties. One response to Menon's paradox rejects non-existent objects, adopts Russell's theory of descriptions, which analyzes statements about non-existent objects as existential statements that happen to be false, and the golden mountain is golden becomes. There exists something that is golden and is a mountain, and this statement is false because no such thing exists. And fictional statements are understood as prefixed by an implicit fiction operator. In the Sherlock Holmes stories, it is true that Holmes is a detective, and this preserves the intuition that Holmes is a detective, in some sense, while avoiding commitment to non-existent objects. And this Russellian approach has been standard in analytic philosophy, is the orthodox view, treats apparent reference to non-existent objects as disguised quantification or as occurring within the scope of intentional operators. Another response defends Menon's theory in modified form, accepts that there are non-existent objects, but restricts what properties they can have, distinguishes between nuclear properties like being golden or being a detective, which non-existent objects can have, and extra nuclear properties like existing or being thought about, which are different, and impossible objects like round squares have both roundness and squareness as nuclear properties, but do not violate contradiction because they do not exist, do not have instances in reality, and their properties do not need to be jointly instantiable. And this neo-Meinongian approach preserves some of Meinong's insights while avoiding Russell's objection, and various philosophers, including Terence Parsons and Richard Routley, have developed sophisticated neo-Meinongian theories that handle the paradoxes. A third response appeals to possible worlds, argues that fictional and non-existent objects exist in other possible worlds, are possible but not actual, and when we talk about Sherlock Holmes, we're talking about a possible person, someone who exists in other possible worlds, in worlds where Conan Doyle's stories are true, and this preserves the intuition that Holmes is a detective, is a real object in some sense, while avoiding the paradox of non-existent objects, because Holmes is not non-existent but merely non-actual, exists in other worlds. And possible worlds semantics provides a framework for understanding modality and fiction without Meinongian ontology. Meinong's paradox also raises questions about what it means to exist, about whether existence is a property like others or is somehow special, and Kant argued that existence is not a real predicate, not a property that objects have or lack, but is the presupposition of having properties. And this Kantian view seems to refute Meinong, seems to show that non-existent objects cannot have properties because having properties requires existing. But Meinongians respond that this assumes existence is necessary for predication, that only existing things can have properties, and this assumption is precisely what Meinong denies. And the debate continues about whether existence is a property and whether objects must exist to have properties. The golden mountain glitters in imagination, non-existent but golden, and Sherlock Holmes solves cases in fiction, non-existent but a detective, and the round square defies logic, non-existent and impossible, and Meinong's theory says these are real objects in the broad sense of being, and the paradox asks how this can be, how nothing can be something, how non-existence can have properties, and the answers divide philosophers, some accepting Meinong's insights, some rejecting them entirely, and the paradox persists as a challenge to theories of reference and ontology, a puzzle about what we talk about when we talk about what does not exist, and whether such talk requires real objects or can be explained without them. And Meinong's paradox endures as one of the strangest and most controversial problems in metaphysics, a problem about the boundary between being and non-being, about what counts as real, and about whether existence is the only kind of reality or whether non-existent objects have their own shadowy realm of being. Nagel's bat problem, why you can never know what it's like to be anything else. A philosopher contemplates a bat hanging upside down in a cave, navigating through echolocation, emitting high-frequency sounds and listening to the echoes, building a sonic map of the world. And the philosopher asks what it is like to be a bat. What is the subjective character of bat experience? What does echolocation feel like from the inside? And philosopher Thomas Nagel argues that no amount of objective information about bat neuroscience, about bat behavior, about the physics of sonar, can tell us what bat experience is like, because subjective experience has an essential first-person character, a what it is likeness that cannot be captured from the third-person objective perspective of science, and the gap between objective description and subjective experience is unbridgeable. And this means that consciousness, at least in its subjective aspect, resists scientific explanation, resists reduction to physical terms. And this is Nagel's bat problem, presented in his famous 1974 paper, What Is It Like to Be a Bat? And the problem illustrates the explanatory gap between physical facts and phenomenal facts, shows that subjective experience involves something that objective science cannot capture and challenges physicalist theories of mind to explain how subjective character could be accommodated within a purely physical framework. Imagine trying to know what echolocation is like, trying to understand bat experience from the inside, and you learn all the objective facts. Learn about the bat's auditory system, about how it processes echoes, about which brain regions are involved. And this knowledge is real, is valuable, tells you how echolocation works, but it does not tell you what it feels like, does not give you access to the bat's subjective experience, to the phenomenology of navigating by sound. And Nagel's point is that this gap is not due to practical limitations, not due to insufficient technology or incomplete knowledge, but is a fundamental gap between objective and subjective perspectives, between what can be known from outside and what can only be known from inside. And no amount of objective knowledge can bridge this gap, can provide access to subjective experience. The bat problem generalizes beyond bats to any creature with a different sensory modality, a different nervous system, a different form of consciousness. And Nagel uses bats because they are mammals, are relatively similar to humans, yet have a sensory mode, echolocation, that humans lack. And this combination makes the example vivid, makes the gap between human and bat experience clear. And if we cannot know what it is like to be a bat, then we certainly cannot know what it is like to be a fish, an insect, an octopus, creatures whose nervous systems and sensory worlds are even more alien. And this suggests that consciousness, in its subjective aspect, is fundamentally private, is accessible only to the being who has it, and different kinds of consciousness are mutually inaccessible, cannot be fully understood from outside. Visualize the subjective character of experience as the view from inside, the first-person perspective, the what it is likeness. And this perspective is essential to consciousness, is what makes consciousness consciousness rather than merely information processing. And Nagel argues that physicalism, the view that everything is physical, must either deny that subjective character exists, which seems false because we all know from our own case that consciousness has a subjective character, or must explain how subjective character could be physical, how objective physical facts could constitute subjective, first-person experiences. And this explanation is what physicalism has not provided, what the bat problem challenges physicalism to provide. One response to the bat problem accepts the explanatory gap, but denies that it shows anything metaphysical, argues that the gap is merely epistemological, is about the limits of what we can know rather than about the nature of reality, and consciousness might be physical, even though we cannot fully understand it from the objective third-person perspective. And just as we cannot know what it is like to be a bat, we also cannot know what it is like to be another human, cannot fully access their subjective experiences, and yet we do not conclude that human consciousness is non-physical. And so the bat problem shows limits of knowledge, but not limits of physicalism, shows that subjective experience has aspects that resist objective description, but not that these aspects are non-physical. Another response argues that future science might bridge the gap, might develop ways of understanding subjective character objectively, might create theories that capture phenomenology in physical terms, and our current inability to imagine how this could be done does not prove that it cannot be done. And Nagel's argument trades on current ignorance, assumes that the gap is permanent when it might be merely temporary, and this response is optimistic about the prospects for physicalist explanations of consciousness, believes that the hard problem and the bat problem will eventually be solved by scientific progress. A third response from Nagel's position argues that the bat problem reveals something deep about the structure of reality, that consciousness has an irreducibly subjective aspect, an aspect that cannot be captured by objective physical description. And this does not mean consciousness is non-physical in the sense of being immaterial or supernatural, but it means that physicalism, as traditionally conceived, is incomplete, misses something essential about consciousness, and a complete theory of reality must include both objective physical facts and subjective phenomenal facts. And these two kinds of facts cannot be reduced to each other. And this position is sometimes called naturalistic dualism, accepts that consciousness is natural, is part of the natural world, but denies that it is reducible to physics. The bat problem also has implications for artificial intelligence, for whether machines could be conscious, because if we cannot know what it is like to be a bat, then we also cannot know what it is like to be a computer, cannot know whether AI systems have subjective experiences, and the bat problem suggests that behavioral evidence is insufficient, that even if a machine passes every behavioral test, exhibits intelligence, responds appropriately to stimuli, we still cannot know whether there is something it is like to be that machine, whether there is subjective experience behind the behavior, and this creates a permanent epistemic barrier, a limit on what we can know about machine consciousness. The bat hangs in the cave, emitting sounds, perceiving the world through echoes, and its experience is alien, is inaccessible to human understanding. And Nagel's question remains, what is it like? And the answer is we do not know, cannot know, because knowing requires access to the subjective perspective, requires being the bat or having the bat's sensory and cognitive capacities, and neither is possible. And so bat consciousness remains a mystery, remains forever beyond human comprehension. And this mystery is not unique to bats but applies to all consciousness, to the fundamental subjectivity of experience, to the what it is likeness that defines phenomenal consciousness. And Nagel's bat problem endures as one of the most influential thought experiments in philosophy of mind, a vivid illustration of the explanatory gap, a challenge to physicalist theories, and a reminder that consciousness, in its subjective aspect, resists objective description, resists scientific reduction, and remains one of the deepest puzzles about the nature of mind and reality. And the bat flies through the cave, navigating by sound, living its bat life, having its bat experiences, and what those experiences are like remains unknown, remains unknowable. And the problem persists, the gap between objective knowledge and subjective experience, the difference between knowing about consciousness and knowing consciousness from the inside. And Nagel's question echoes, what is it like to be a bat? And no answer comes, no answer can come, and the problem stands as a permanent marker of the limits of objective understanding, the irreducible subjectivity of experience and the mystery at the heart of consciousness. Morton's fork, when both choices lead to the same doom. A tax collector in 15th century England faces a dilemma when assessing how much wealthy citizens should pay, and the collector observes that some nobles live extravagantly, displaying their wealth openly, and others live frugally, claiming poverty. And Archbishop John Morton, serving as Lord Chancellor under King Henry VII, devises a strategy to extract taxes regardless of which lifestyle the noble chooses, and the strategy is simple and brutal. If a noble lives extravagantly, then clearly they have money and can afford to pay high taxes. And if a noble lives frugally, then clearly they are saving money and must have accumulated wealth and can afford to pay high taxes. And either way, the noble must pay. There is no escape, no strategy that avoids taxation. And this trap, where two apparently opposite choices lead to the same unwanted outcome, became known as Morton's fork, named after the archbishop who wielded it. And the term has entered common usage to describe any situation where someone must choose between two options that both lead to the same undesirable result, where the appearance of choice masks the reality of inevitability. Imagine being a noble in Morton's England, weighing your options, trying to decide whether to live well or live simply, and realizing that either choice leads to heavy taxation, that the tax collector has closed off all escape routes, has constructed a logical trap where your strategy is irrelevant, where you lose regardless of what you choose. And this creates a sense of futility, a recognition that the game is rigged, that the appearance of agency is illusory, and Morton's fork exemplifies a class of situations where apparent choices are not genuine choices, where different paths converge on the same destination, and the only real choice is whether to accept the inevitable or to refuse to play the game at all. The structure of Morton's fork appears throughout logic, rhetoric, and strategy. Wherever someone constructs an argument that covers all cases, that shows that regardless of what premises are accepted, a certain conclusion follows, and such arguments can be powerful tools of persuasion, can trap opponents in positions where they cannot escape the conclusion, but they can also be fallacious, can hide implicit assumptions or false dichotomies, can present apparent inevitability that dissolves under scrutiny. And distinguishing genuine Morton's forks from apparent ones requires careful analysis of whether the two paths really do lead to the same conclusion, or whether there are hidden differences, hidden escape routes. Visualize the fork as a Y-shaped path, two branches diverging, one path representing extravagance and one representing frugality, and both paths lead to the same destination. The tax collector's office and the noble walking either path arrives at the same place. And the fork is not a choice between outcomes, but a choice between routes to a predetermined outcome. And the futility comes from recognizing that movement, that action, that strategy, all are pointless, all lead to the same end, and the only way to avoid the destination is to refuse to walk, to opt out of the entire framework. Morton's fork differs from a dilemma, where two choices lead to different, undesirable outcomes, and the chooser must select the lesser evil, because in Morton's fork, the outcomes are the same, are equally bad, and the choice is between different routes to that bad outcome. And this makes Morton's fork particularly frustrating, particularly demoralizing, because at least in a dilemma there is a meaningful choice, a decision that matters, but in Morton's fork the choice does not matter. The outcome is fixed, and the appearance of choice is a cruel illusion. The concept has applications in game theory, in situations where a player's strategies are dominated, where regardless of what the player does, the outcome is worse than some alternative the player cannot access, and recognizing Morton's forks is important for strategic reasoning, for understanding when continued play is pointless, when the game should be abandoned rather than played, because playing only wastes resources without changing the outcome. Morton's fork also appears in legal and political contexts, where laws or policies are designed to be inescapable, where any action a person takes falls under the law's scope, and this can be legitimate, can reflect comprehensive regulation of a domain, but it can also be oppressive. It can create situations where individuals have no legal way to avoid a burden, no option but compliance, and recognizing such structures is important for identifying injustice, for understanding when law has become a trap rather than a framework for freedom. The paradox also has psychological dimensions, because facing Morton's fork creates learned helplessness, creates the sense that choices do not matter, that outcomes are predetermined regardless of effort or strategy, and this can lead to resignation, to ceasing to resist, to accepting the inevitable, and oppressive systems often work by creating Morton's forks, by ensuring that resistance and compliance lead to similar outcomes, that fighting and surrendering are equally futile, and breaking out of Morton's fork requires either finding a hidden third option, a way to refuse the binary choice, or accepting one path and finding meaning in the choosing, even if the outcome is fixed. Some philosophers argue that life itself is Morton's fork, that all paths lead to death, that whether we live virtuously or wickedly, happily or miserably, we end up in the same place, non-existent, and this can be a source of nihilism, can undermine the sense that choices matter, but it can also be liberating, can free us to choose based on values rather than outcomes, to recognize that if all paths lead to death, then what matters is the path itself, the journey, not the destination, and Morton's fork becomes an invitation to find meaning in process rather than result. The Archbishop's strategy was effective, was brutal, extracted taxes efficiently, and the nobles paid, unable to escape the logic, unable to find a strategy that avoided the fork. And Morton's fork entered history, became a term of art, became a warning about inescapable traps, about situations where apparent choice conceals actual constraint, and the fork remains present in contemporary debates about policy, law, and strategy. A reminder that not all choices are meaningful, that sometimes the appearance of freedom masks the reality of compulsion, and that recognizing Morton's fork is the first step toward escaping it, toward finding the third option, the refusal to engage, the rejection of the binary. And the fork stands, points in two directions, both leading to the same place, and the challenge is to see the fork for what it is, to recognize when choice is illusory, when strategy is futile, and when the only real option is to walk away, to refuse the fork entirely, to create a new path that the fork's designer did not anticipate. And Morton's fork remains a timeless trap, a logical structure that appears whenever someone seeks to eliminate all escape routes, to ensure that whatever choice is made, the desired outcome follows. And the fork endures as a reminder that the appearance of choice can be deceptive, that freedom requires more than options, requires that options lead to genuinely different outcomes, and that when options converge, when the fork's prongs meet, choice becomes meaningless, and only opting out restores agency. More's open question, argument why good cannot be defined. A philosopher claims to have defined goodness, claims that good means pleasure, or good means what evolution favoured, or good means what most people approve of, and the definition is offered with confidence, with arguments and evidence supporting it, and yet G.E. Moore, in his 1903 book Principia Ethica, pointed out a fatal problem with all such definitions, a problem so simple and devastating that it has shaped ethics ever since. And the problem is this: take any proposed definition of good, any equation of goodness, with some natural property, and you can always ask a meaningful question. You can ask, but is that property itself good? And the fact that this question remains open, remains intelligible, and not obviously silly, shows that the definition has failed, shows that good has not been captured by the natural property. And this is More's open question argument, a challenge to naturalistic definitions of good that attempts to prove that goodness is indefinable, that it cannot be reduced to any natural fact or property, that it is a simple, unanalyzable concept that we grasp directly through moral intuition but cannot explain in other terms. Imagine someone says good means pleasant, pleasure is what good is, and now More asks the open question, but is pleasure good? And this question makes sense, is not absurd, is not like asking whether bachelors are unmarried men, where the question is trivially answered by the definition. And the fact that we can meaningfully ask whether pleasure is good shows that good does not mean the same thing as pleasant. Otherwise, the question would be equivalent to asking whether pleasant things are pleasant, which is a meaningless tautology. And since the question is not meaningless, since we can intelligently disagree about whether pleasure is good, the definition must be wrong, must have failed to capture what goodness really is. The same argument applies to any naturalistic definition. If someone says good means evolutionarily advantageous, we can ask, but is what evolution favoured good? And this is an open question. Many people would say no, that evolution produces traits that help survival and reproduction, but not necessarily traits that are morally good, that rape and infanticide might be evolutionarily advantageous in some contexts, but are not good, and so the definition fails. Or if someone says good means desired by most people, we can ask, but is what most people desire good? And again, this is open. We can imagine societies where most people desire things that are actually bad, where popular opinion is mistaken, and so the definition fails again. More concluded that good is indefinable, not because we do not know what it is, but because it is a simple, primitive concept, like yellow or existence, something that cannot be broken down into simpler parts or explained in other terms, but must be grasped directly. And we know good through moral intuition, through a kind of perception that is not sensory but intellectual. And different people's intuitions might disagree, but that does not mean goodness is subjective. It might mean that some people perceive moral reality more clearly than others, just as some people have better colour vision, and More's position is a form of non-naturalism, the view that moral properties are real but not natural, not part of the physical world studied by science, but a distinct realm of normative facts that exist objectively. The open question argument has generated enormous controversy. Critics argue that it proves too much, that the same reasoning would show that nothing can be defined, because for any definition, we can ask an open question. If water is H2O, we can ask, but is H2O water? And before we learned the chemistry, this question was open. People could meaningfully disagree, and yet we now accept that water is H2O as a correct identity. Not a definition of meaning, but an empirical discovery about what water turns out to be. And perhaps good is like this. Perhaps good is identical to some natural property, not as a matter of meaning, but as an empirical fact about what goodness turns out to be. And the open question shows only that we have not yet discovered which natural property good is, not that no such property exists. Others argue that the open question argument assumes too much about how meaning works, assumes that if two terms mean the same thing, then they must be obviously synonymous. But this is false. Morning star and evening star both refer to Venus, but it was not obvious. People could meaningfully ask whether the morning star is the evening star. And so More's test fails. The fact that a question is open does not prove that the terms do not refer to the same thing. And so the open question argument does not establish that good is indefinable, only that the definition is not obvious, not transparent. And this leaves room for naturalistic theories that identify goodness with some natural property as an empirical discovery rather than a conceptual analysis. Visualize More's argument as a test applied to proposed definitions. Each definition is presented. Good equals X, and More applies the test. He asks, is X good? And if the question is intelligible, if it makes sense to ask, if competent speakers can understand the question and disagree about the answer, then the definition fails. X does not capture what good means. And More applies this test to definition after definition. Hedonism says good equals pleasure. More asks, is pleasure good? The question makes sense. Test failed. Naturalism says good equals natural property. Why? More asks, is why good? The question makes sense. Test failed. And the test seems to show that no natural property can be identical to goodness. That good resists reduction, resists naturalization, stands apart from the world of facts, and refers to something normative, something that cannot be captured by descriptive language. The argument has implications for metaethics, for the question of what kind of thing goodness is. If More is right, then moral realism, the view that moral facts exist objectively, must be non-naturalist, must accept that moral properties are sui generis, distinct from natural properties, irreducible to physics or biology or psychology. And this raises questions about how we can know moral facts, how moral properties relate to natural properties, whether moral facts can cause anything or play any role in explaining behaviour. And non-naturalism faces challenges, struggles to explain how we perceive non-natural properties, how they fit into a scientific worldview, whether they're compatible with naturalism about everything else. The open question argument also influenced emotivism and expressivism, non-cognitivist views that deny moral statements are factual claims at all, argue instead that moral language expresses attitudes or emotions rather than describing reality, and these views claim to explain why the open question is always open, because good does not refer to any property, natural or non-natural, but expresses approval or prescribes action. And so asking whether X is good is asking whether to approve of X, whether to pursue it. And this is always an open question. always something we can meaningfully deliberate about. But the non-cognitivists deny More's conclusion, deny that goodness is a real property we intuit, argue instead that moral language has a different function, is not in the business of describing reality, but of expressing commitments and guiding action. More's argument changed the landscape of ethics, forced philosophers to take seriously the question of whether moral properties are natural or non-natural, whether moral knowledge is empirical or a priori, whether ethics can be reduced to science or remains a distinct domain, and the argument remains controversial. Some see it as a decisive refutation of naturalism. Others see it as a confusion about meaning and reference. And the debate continues, with naturalists proposing sophisticated identities between moral and natural properties, with non-naturalists defending irreducible normativity, and with non-cognitivists denying that moral language describes properties at all. And More's open question sits at the center of these disputes. A simple test that reveals deep issues about meaning, about value, about the relationship between facts and norms, and about whether goodness is something we discover in the world or something we project onto it. And the question remains open, always open, because that is what good does. It resists definition, resists reduction, remains stubbornly normative, always inviting the question, but is that really good? And no answer closes the question, no definition settles it. And More's argument endures as a reminder that ethics is not reducible to any other domain, that the normative cannot be fully naturalized, and that goodness, whatever it is, stands apart, indefinable, and irreducible, a primitive concept that we use, but cannot explain. Maxwell's demon, the tiny creature that could break the universe. Imagine a box divided into two halves by a partition. The partition has a small door, operated by a tiny intelligent being, a demon as physicist James Clerk Maxwell called it in 1867. And the box contains gas molecules bouncing around randomly, some moving fast and some moving slow. Hot molecules and cold molecules mix together, and the demon, perched at the door, watches the molecules approach and makes decisions. When a fast-moving hot molecule approaches from the left, the demon opens the door and lets it pass to the right. And when a slow-moving cold molecule approaches from the right, the demon opens the door and lets it pass to the left. And when molecules moving in the wrong directions approach, the demon keeps the door closed. And over time, this sorting process concentrates hot molecules on the right side and cold molecules on the left side, creating a temperature difference without any energy input, just the demon's intelligence and careful timing. And once a temperature difference exists, it could be used to run a heat engine, to extract work, to power machines. And this seems to create energy from nothing, seems to violate the second law of thermodynamics, which states that entropy always increases, that heat flows from hot to cold, and never the reverse without work being done. And so, Maxwell's demon presents a paradox, a thought experiment, where intelligence appears to defeat fundamental physical law, where information and cleverness seem to allow perpetual motion. And this puzzle troubled physicists for over a century, until the resolution emerged from understanding the relationship between information and thermodynamics. Visualize the demon at work, watching molecules approach, each molecule carrying kinetic energy, moving at some velocity determined by temperature. And the demon perceives each molecule, measures its speed, decides whether to open or close the door, and executes the decision perfectly. And after many such operations, the gas on the right is hotter than the gas on the left. Entropy has decreased in the gas. Order has emerged from disorder, and this seems impossible because the second law of thermodynamics is supposed to be universal, supposed to apply to all closed systems, and the box with the demon should be a closed system. No energy enters or leaves, and yet entropy decreases, and if entropy can decrease, then the second law is violated, and if the second law can be violated, then all of thermodynamics collapses. Heat engines could run at impossible efficiencies, refrigerators could cool without power input, the universe's arrow of time could reverse, and physics as we know it breaks down. The resolution emerged gradually through the work of several physicists, including Leo Szilard, Leon Brillouin, and Charles Bennett, and the key insight is that the demon must gather information about the molecules, must measure their velocities, must store this information in memory, and these operations have thermodynamic costs. The demon's brain or computer or measuring device must interact with the molecules to measure them, and this interaction dissipates energy, and more importantly, the demon's memory fills up with information about past measurements, and eventually the memory must be erased to make room for new measurements. And Rolf Landauer proved in 1961 that erasing information has a fundamental minimum thermodynamic cost. Erasing one bit of information requires dissipating at least a certain amount of heat proportional to temperature. And this heat generation increases the entropy of the environment. And when the entropy increase from information erasure is included in the accounting, the total entropy of the system plus demon never decreases. The second law is preserved. The demon cannot create a perpetual motion machine because the cost of gathering and erasing information exactly compensates for the entropy decrease in the gas. Imagine the demon's memory as a tape with bits that record whether each molecule was fast or slow, and as the demon sorts molecules, the tape fills up. 0 for slow molecule, 1 for fast molecule, and the tape grows longer and longer, and eventually the demon runs out of memory space and must erase the tape to continue operating. And the erasure process, Landauer showed, must dump heat into the environment, must increase entropy elsewhere, and the entropy increase from erasure is at least as large as the entropy decrease from sorting, and so the net change in entropy is 0 or positive, never negative. And the second law holds: the demon cannot beat thermodynamics. Intelligence and information do not provide a loophole. They are themselves subject to thermodynamic constraints, and information is physical, has energy costs, has entropy, and cannot be manipulated freely without thermodynamic consequences. The paradox and its resolution have profound implications for computer science, for the theory of computation, for the relationship between information and physics. Because Landauer's principle establishes that computation has fundamental physical limits, that there is a minimum energy cost for irreversible operations like erasing bits, and this cost sets a lower bound on the energy consumption of any computer. And it explains why computers generate heat, why data centers require enormous cooling systems, why information processing is not free, and it unifies information theory and thermodynamics, showing that bits and entropy are connected, that forgetting information has thermodynamic consequences, that memory erasure increases disorder in the universe. Maxwell's demon also appears in discussions of the arrow of time, the question of why time flows forward, why we remember the past but not the future, why causes precede effects. And the second law of thermodynamics provides an answer: entropy increases, and this increase defines a direction for time. And if Maxwell's demon could violate the second law, then the arrow of time could reverse, the past and future could become symmetric, and the resolution of the demon paradox reinforces the second law, confirms that entropy really does always increase when all systems, including observers and their memories, are accounted for. And this grounds the arrow of time in fundamental physics, connects our subjective experience of time's flow to objective thermodynamic processes. The demon has also inspired practical research into nanoscale systems and molecular machines, because modern technology approaches the scale where Maxwell's demon scenarios become relevant, where individual molecules can be manipulated, where quantum effects and thermal fluctuations dominate, and researchers have built experimental realizations of Maxwell's demon using feedback control, using sensors and actuators to sort particles or extract work from thermal fluctuations. And these experiments confirm Landauer's principle, confirm that information processing has thermodynamic costs, and they explore the limits of miniaturization, the minimum size and energy consumption of computers, and the ultimate efficiency of engines and refrigerators. The tiny demon sits at the door, watching molecules, sorting them, concentrating energy, and for a moment it seems to defeat the second law, seems to create order from chaos. But the illusion fades when the full system is considered, when the demon's memory and the information it gathers are included, when the cost of erasure is accounted for, and the second law stands, unbroken, universal, and the demon, far from being a threat to thermodynamics, becomes a tool for understanding it. A thought experiment that revealed deep connections between information and entropy, between computation and physics, between what we know and what we can do, and Maxwell's demon endures, not as a paradox, but as a solved problem with profound implications, a puzzle that took over a century to fully resolve, and a reminder that even the most abstract thought experiments can illuminate fundamental truths about the physical world, about the nature of information, about the limits of what is possible, and about the deep unity between different branches of physics, between thermodynamics and information theory, between entropy and knowledge. And the demon remains, a fixture in physics pedagogy, a symbol of the power of thought experiments, and a monument to the principle that information is physical, that knowledge has costs, and that nothing, not even intelligence, escapes the iron laws of thermodynamics. Olbers's paradox: why the night sky is dark when it should blaze with light. Look up at the night sky and you see darkness, scattered stars against a black background, empty space between the points of light. And this seems natural, seems obvious. The sky's dark because there are not many stars, because most of space is empty. But in an infinite, eternal universe filled with stars, this darkness becomes paradoxical, becomes something that should not exist. And this is Olbers' paradox, named after German astronomer Heinrich Wilhelm Olbers, who discussed it in 1823, though the puzzle was recognized earlier by others, including Johannes Kepler and Edmund Halley. And the paradox asks why the night sky is dark, when simple reasoning suggests it should be blazing bright as the surface of the sun in every direction. The argument proceeds as follows. If the universe is infinite in spatial extent and has existed forever, and if stars are distributed roughly uniformly throughout this infinite space, then every line of sight from Earth, extended far enough, must eventually intersect the surface of a star, because in an infinite universe, with infinite stars, every direction contains a star somewhere along that sight line, perhaps nearby or perhaps trillions of light years away, but somewhere, and so the entire sky should be covered with stellar surfaces, should glow with the brightness of a star, and there should be no dark spaces, no black background, only light. And yet we see darkness. We see mostly empty space with occasional bright stars. And this contradiction is Olbers' paradox. Visualize the reasoning more carefully. Imagine dividing the universe into concentric shells around Earth, like layers of an onion, each shell at a different distance, and count how many stars are in each shell. A shell at distance r has volume proportional to r squared times the shell thickness, because the surface area of a sphere grows as r squared. And if stars are uniformly distributed, then the number of stars in the shell is proportional to r squared. But the brightness of each individual star falls off as 1 over r squared due to the inverse square law of light. Light spreads out as it travels. And so the total brightness contributed by all stars in a given shell is the number of stars times the brightness per star, which is r squared times 1 over r squared. And these factors cancel, and each shell contributes the same total brightness regardless of distance. And since there are infinitely many shells in an infinite universe, the total brightness is infinite, and the sky should be infinitely bright. And even if we account for stars blocking each other, eventually every sight line intersects a star, and the sky should glow uniformly with the brightness of stellar surfaces. The resolution of Olbers' paradox involves recognizing that the universe is not infinite and eternal in the way the paradox assumes. Modern cosmology tells us that the universe has a finite age, about 13.8 billion years, and light travels at a finite speed, and so we can only see light from stars within our observable horizon, stars whose light has had time to reach us. And this limits the number of stars we can see. And more importantly, the universe is expanding, and distant stars are receding from us, and their light is redshifted, stretched to longer wavelengths and lower energies by the expansion of space. And this redshift dims distant starlight. And for sufficiently distant stars, the redshift is so extreme that their light is shifted into the infrared or radio spectrum, invisible to our eyes. And the combination of finite age and cosmological expansion means that only a finite amount of starlight reaches us, and the night sky is dark. Not because stars are sparse, but because the universe has not existed long enough for light from all stars to reach us, and because expansion dims the light from distant sources. Another factor is the finite lifetime of stars. Stars are not eternal. They form, they shine for millions or billions of years, and they die. And in a finite age universe, not all regions have had time to form stars, and not all stars have been shining throughout cosmic history, and so the background radiation from stars is further reduced. And these factors combine to ensure that the night sky is dark despite the vast number of stars in the universe. The paradox also touches on thermodynamics and equilibrium, because if the universe were infinite, eternal, and static, with stars distributed uniformly, then eventually the radiation from all these stars would fill space uniformly. Space would reach thermal equilibrium with stellar surfaces, and everything would be at the same temperature as the surface of a star, about 6,000 degrees Kelvin, and Earth would be vaporized, life would be impossible, and the darkness of the night sky is evidence that the universe is not in thermal equilibrium, is not static and eternal, but is instead dynamic, expanding, and young. Olbers' paradox played a role in the development of modern cosmology. It was one piece of evidence that the universe cannot be static and eternal, that something must be different about the large-scale structure of space and time. And when Edwin Hubble discovered in the 1920s that the universe is expanding, that distant galaxies are receding from us, this provided a natural resolution to Olbers' paradox. The expansion redshifts and dims distant light, preventing the accumulation of infinite brightness, and the finite age of the universe, confirmed by observations of the cosmic microwave background and the distribution of galaxies, completes the resolution, ensuring that we see only a finite amount of cosmic history, only the light from stars within our past light cone. The paradox also has poetic resonance. It asks why there is darkness, why night exists, why space is not filled with light. And the answer is that darkness is a consequence of time and change, of the universe having a beginning, of stars being born and dying, of space expanding and carrying light away. And darkness becomes not an absence, but a presence, not a void, but a canvas. Evidence of cosmic history, evidence of the dynamic evolving universe we inhabit. And the dark night sky, far from being empty or boring, is rich with information. Tells us about the finite age of the cosmos, about the expansion of space, about the distribution and evolution of stars and galaxies, and Olbers' paradox, resolved but not forgotten, remains a reminder that even simple observations, like the darkness of night, can contain profound mysteries, can require deep theories to explain, and can reveal fundamental truths about the nature of the universe. The stars shine against the darkness, scattered lights in an empty sky, and the darkness itself is meaningful, is informative, is the signature of a finite age expanding universe. And Olbers' paradox, resolved by modern cosmology, endures as a teaching tool, as an illustration of how seemingly simple questions can have complex answers, and as a monument to the human capacity to wonder about the ordinary, to see puzzles where others see only the familiar, and to pursue those puzzles until the universe reveals its secrets. Hilbert's Hotel Paradox. A hotel with infinitely many rooms, each numbered with a positive integer, 1, 2, 3, and so on without end, stands fully occupied. Every room contains a guest, and yet when a new guest arrives, the manager is not concerned, does not turn them away, because infinity accommodates addition in ways that finite quantities cannot. And the manager simply asks each current guest to move to the next room. The guest in room 1 moves to room 2. The guest in room 2 moves to room 3, and so on, each guest shifting one room higher. And this process, applied simultaneously to all guests, leaves room 1 vacant, and the new arrival is accommodated without displacing anyone permanently. And this is Hilbert's Hotel, a thought experiment devised by the mathematician David Hilbert to illustrate the counterintuitive properties of infinite sets, to show that infinite collections behave in ways that violate ordinary intuition, that they can be put in one-to-one correspondence with proper subsets of themselves, that adding elements or removing elements does not change their cardinality, and that the whole is not always greater than the part when dealing with infinity. The paradox deepens when an infinite number of new guests arrive, an infinite bus pulling up to the hotel, each passenger needing a room. And again, the manager is unperturbed, because there is a strategy to accommodate everyone. The manager asks each current guest in room N to move to room 2N. The guest in room 1 moves to room 2. The guest in room 2 moves to room 4. The guest in room 3 moves to room 6, and so on. And this process places all the original guests in the even-numbered rooms, leaving all the odd-numbered rooms vacant. And since there are infinitely many odd-numbered rooms, one for each positive integer, there is exactly enough space for the infinitely many new arrivals, who are assigned to rooms 1, 3, 5, and so on. And the hotel, despite being full, has accommodated an infinite number of additional guests without anyone being displaced. The paradox reveals that infinite sets have a property called countable infinity. They can be placed in one-to-one correspondence with the natural numbers, and this correspondence allows for operations that seem impossible with finite sets. A fully occupied hotel with finitely many rooms cannot accommodate additional guests without evicting someone. But a fully occupied hotel with infinitely many rooms can accommodate not just one additional guest, but infinitely many. And this does not mean the hotel was not really full before. All rooms were occupied, but rather that fullness does not prevent expansion when infinity is involved, that the concepts of full and empty take on new meanings in the infinite context. Hilbert's Hotel also allows for even stranger scenarios. Suppose infinitely many infinite buses arrive, each bus containing infinitely many passengers, and the hotel must accommodate all of them. And again, there is a strategy. The manager can use a pairing function, a mathematical technique that assigns a unique room number to each combination of bus number and seat number, ensuring that every passenger gets a unique room. And the hotel, starting from full occupancy, can expand to accommodate not just countably many new guests, but countably many groups of countably many new guests. Because the union of countably many countable sets is still countable, and so the total number of guests, after all the buses are accommodated, is the same cardinality as the number of guests before. Both are countably infinite. Both can be placed in one-to-one correspondence with the natural numbers. The paradox challenges intuitions about size, quantity, and comparison, because it shows that infinite sets can be proper subsets of themselves and yet have the same cardinality. The even numbers are a proper subset of all natural numbers, missing all the odd numbers, and yet there are just as many even numbers as natural numbers. Both sets are countably infinite, and this violates the Euclidean principle that the whole is greater than the part, a principle that holds for finite sets but fails for infinite sets. And this failure is not a contradiction, but a distinctive feature of infinity, a marker that distinguishes finite from infinite. Hilbert's hotel also raises questions about the physical realizability of actual infinities, because while the mathematics of infinite sets is well defined and consistent, whether actual infinite collections exist in the physical world is contested. Some philosophers and physicists argue that only potential infinities exist, processes that can continue indefinitely but never reach completion, while actual infinities, completed infinite totalities, are merely mathematical. Abstractions and the hotel paradox, with its fully occupied infinite structure, represents an actual infinity, and if such infinities cannot exist in reality, then the paradox is merely a mathematical curiosity without physical significance. But others argue that the universe may be spatially infinite, that time may extend infinitely into the past or future, and that quantum field theory involves infinite dimensional spaces. And if actual infinities are physically real, then the strange properties illustrated by Hilbert's hotel may have real-world counterparts. The hotel also appears in theological discussions about divine attributes, because an omnipotent being might be thought to perform tasks that involve manipulating infinite collections. And Hilbert's hotel shows that such manipulations are logically coherent, that infinity does not lead to contradiction, that an infinite hotel can be fully occupied and yet accommodate more guests. And this addresses worries that infinity is inherently paradoxical or incoherent, demonstrating that infinite structures follow consistent rules, even when those rules differ from finite intuitions. The hotel stands infinitely tall, infinitely long, each room numbered, each room occupied, and the new guest arrives. And there is room, always room, because infinity plus one is infinity, because infinity plus infinity is infinity, because the operations of addition and union that exhaust finite resources leave infinite resources unchanged, and the paradox reveals the strangeness of infinity, the way it defies expectation, the way it makes possible what seems impossible, and Hilbert's hotel remains one of the most vivid and accessible illustrations of this strangeness, a story that captures in simple terms the profound weirdness of the infinite. And mathematicians use it to teach, to explain cardinality, to distinguish countable from uncountable infinities, to motivate Cantor's diagonal argument and the hierarchy of infinities. And philosophers use it to probe intuitions about existence, about the difference between actual and potential infinity, about whether the physical world contains or could contain infinite structures. And the hotel endures, a fictional place that illuminates real mathematics, a thought experiment that has become a permanent fixture in discussions of infinity, a paradox that is not a contradiction, but a revelation, a demonstration that infinity is not merely a large finite number, not merely an extension of ordinary quantity, but something qualitatively different, something that requires new concepts, new intuitions, and new ways of thinking about size, about number, about what it means for something to be more or less equal or unequal, full or empty. And the guests check in, infinitely many guests, and there is always room for more.